Dear students, welcome to the session on Complex Integration Basics Part 2. In the previous session, we learned the basics. We recall what is meant by analytic function, entire function, and then we learned the definition of singular points and we see some examples how to find the singular point. In today's session, we are going to learn how to sketch the region and check whether the singular point lies inside the region or lies outside the region. Let us take an example. Sketch the region and find the singular points for mod z equal to 1 by 2. The given region is mod z equal to 1 by 2. First of all, we have to understand in the complex plane, mod z equal to r is a circle with center 0, 0, radius r. Let us see mod z is equal to r. We know that z is x plus iy. Also we know that modulus of x plus iy is square root of x square plus y square is equal to r. Therefore, x square plus y square is equal to r square. Here the general formula for circle is x minus a whole square plus y minus b whole square is equal to r square. Therefore, the center is a comma b. According to our problem, we have x minus 0 whole square plus y minus 0 whole square is equal to r square. So the center is 0, 0 and my radius is r. So for this problem, mod z is equal to 2, my center is 0, 0 and my radius is 1 by 2. So you can easily found the center and radius. Now we have to draw the figure. Just draw a approximate circle. The radius is going to be 1 by 2, center 0, 0 and points are 1 by 2, 0 here, 0, 1 by 2. This is my given region. Next we have to find the singular points. From the question, it is very clear my numerator is constant. It is an analytic function. Moreover, it is an entire function. We see all the details in the first part of the basic video. Now we have to deal with the denominator. To find the singular point, take the denominator, equate it to 0. Once we equate it to 0, we get the points are 1 and 2. It is very clear that the singular points are 1 and 2. Now, if it is z equal to 1, I can rewrite this as x plus iy is equal to 1. Very particularly, I can write this as 1 plus I0. Therefore, the point x comma y is 1 comma 0. Similarly, if z is equal to 2, I can write it as x plus iy is equal to 2 plus I0. Therefore, the point is 2 comma 0. So now I will take z equal to 1. The point is 1 comma 0. Since my radius is 1 by 2, that is 0.5, my 1 comma 0 will lies outside the circle. So z equal to 1 is a singular point that lies outside C. Similarly, z equal to 2 means the point is 2 comma 0. This is also lies outside the circle because the radius length is 1 by 2. So both singular points lies outside C. We have another way to find the singular points either lies inside or outside C. For this, we are going to consider mod z is equal to r. If mod z less than r, then the singular point lies inside. If mod z is equal to r, the point lies on the curve. If mod z is greater than r, the point lies outside. So according to our problem, mod z is 1 by 2. Now I am going to take the left hand side. Mod z. At the point z equal to 1, mod z is equal to modulus of 1, that is 1. If it is greater than my radius 1 by 2, then the point lies outside. Similarly, for the point z equal to 2, mod z is equal to modulus of 2, that is 2. 2 is greater than 1 by 2. Therefore, z equal to 2 is a singular point, lies outside C. You can see the typed version. Now, in the same problem, I am only changing the radius as 1.5 or 3 by 2. It is very easy. Center is 0, 0. Radius is 3 by 2. I can easily draw the circle. Now we can mark the limited points which is needed for the problem solving. We already know the singular points. Now, z equal to 1, that is 1 comma 0. Since the radius is 1.5, 1 comma 0 lies inside C, and z equal to 2, that is 2 comma 0, it lies outside because the radius is 1.5. So z equal to 2 is a singular point, lies outside C. In the method 2, we have to take LHS. So at z equal to 1, mod z is equal to modulus of 1, that is less than 3 by 2. If it is less than 3 by 2, the singular point is lying inside C. The next singular point, z equal to 2. Modulus of 2, that is 2 greater than 3 by 2. Therefore, the singular point lies outside C. Hope you understand. In the similar way, suppose I am increasing the radius, mod z equal to 3. The given region is mod z equal to 3, radius is 3, center 0, 0. Therefore, we can easily draw the circle. And my singular points are z equal to 1 and 2. Now, z equal to 1, that is 1, 0, obviously lies inside the circle. The next point z equal to 2, it is going to be 2, 0. This is also lie inside the circle. In this case, both singular points z equal to 1 and 2 lies inside C. In the second method, we just take the LHS at z equal to 1, mod z is equal to modulus of 1, it is less than 3. Therefore, the singular point lies inside C. Next, at z equal to 2, we have modulus of 2, that is 2. Still it is less than 3. So, the second point z equal to 2 also lies inside C. From this three problems, hope you get a clear visualization how to sketch the region, how to find the singular points, and whether they lie inside or outside C. Next, we are going to see few formulas and theorems, which is very much helpful in problem solving. In our school days, we learned the definite integral over a to b f of x dx. The path is fixed along the x-axis. But now, in complex integration, we use integral over c f of z dz. Here, the path c can be any curve in the complex plane. Next, we are going to learn what is contour. I'm not going into very deep concepts. We just take whichever is needed for our problem solving. A contour is just a path in the complex plane. Next, we are going to learn a simple closed contour. A simple closed contour is a loop. It never crosses itself. Suppose I am taking a curve like this. At this point, it crosses itself. So if a loop is simple closed contour, it should not cross itself. The starting point and ending point should be the same. If you take a circle, the starting and ending point are same, and it should travel in the counterclockwise direction. We say it as positive sense or simply positive. Now we can see the pictorial representation. Circle is a simple closed contour because it never crosses itself. Then the starting point and ending point of circle is same, and the direction is counterclockwise direction. So it is a simple closed contour. We can see few examples. Just now we see circle is the simple closed contour. Similarly, rectangle is also a simple closed contour. But if you take a curve like this, it crosses itself, so it cannot be simple closed contour. The second one is open, it is not closed. For Cauchy's theorem, we need only a simple closed contour. Next, we are going to see what is meant by simply connected region and multiply connected regions. A region is said to be simply connected region. It should not have any holes. For example, you can see this image. It can be easily shrinked to a point. A region is multiply connected region. It has one or more holes. Here, we cannot shrink this to make a point. We can have a visualization. If it has no holes, I can contract it to a point. For a multiply connected region, it has holes, so I cannot shrink this. You can see the definition of simply connected and multiply connected domains, and we can see few figures for simply connected region and multiply connected regions. Now let us go into the definition of Cauchy integral theorem. If f of z is analytic everywhere inside and on a given simple closed contour C, then integral over C f of z dz is equal to 0. That means there is no singular points or singularities lies inside the simple closed contour C. In curiosity, suppose if we have a singular point which lies inside the contour C, then how to tackle this? For this, next we are going to learn Cauchy integral formula. Suppose we take f of z is analytic function. If you try to integrate f of z divided by z minus a, now the problem comes because z equal to a is a singular point and a lies inside the contour C, then the answer cannot be 0 anymore. So we get some non-zero value in the right hand side. Let us see the definition of Cauchy integral formula. If f of z is analytic inside and on a simple closed contour C taken in a counterclockwise direction or positive sense, then integral over C f of z divided by z minus a into dz is equal to 2 pi I into f of a. Next we are going to see Cauchy integral formula for derivatives. Integral over C f of z divided by z minus a whole power n plus 1 dz is equal to 2 pi I divided by n factorial into n derivative of the function f of z substituted by the value a. For n equal to 1, we get integral over C f of z divided by z minus a whole square dz 2 pi I divided by 1 factorial into f dash of a. Since 1 factorial is simply 1, we write this as 2 pi I into f dash of a. When we substitute n equal to 0, then we get our Cauchy integral formula. Hope you understand, students. So using these formulas, in the next session we are going to solve problems on Cauchy integral theorem as well as Cauchy integral formula.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.